So our first speaker is a mathematician whose work is so creative that his colleagues have compared it to the Lord of the Rings trilogy. Martin Heirer is a professor of mathematics at Imperial College London since 2017. Previously, he has been at the University of Warwick and at the Courant Institute of New York University. He's one of the world's leaders in the field of stochastic analysis. And he has been awarded a number of major mathematical honors and prizes, including the Fields Medal in 2014. And he is also a fellow of the Royal Society. Professor Heirer will speak about bridging scales, and let's welcome him.
Thank you very much. Well, before I start, I'd like to say that I'm very grateful to Pierre for having asked me to speak here. It's a really nice event, though he probably mostly selected me because I'm one of the few francophones in the department. So today what I'm going to talk about is, so the title of the talk is, as you see, is Bridging Scales, is to some extent how do you go from microscopic description, random description of a system to sort of more large-scale macroscopic sort of description. And at the very beginning, I thought I'd start by reminding you sort of the general principles that arise in probability theory. So in probability theory, you see, you always tend to think of, or maybe more general public tends to think of probabilists as people who sort of manage to shake some probabilities out of a hat that kind of magically allow to predict what's the probability of something. And of course, that's absolutely not true because otherwise we'd all be rich in the stock market. What probabilists do is more like sort of transforming or manipulating probabilities. And this means that you still have to start from somewhere. And there are two main principles that allow you to, that guide you in saying, what do you actually start from. And the first one, as so often in mathematics, is symmetry. Okay, so what symmetry says is that essentially if you have an experiment where the outcome is random and there are several possible outcomes and you can distinguish them, but from the perspective of the mechanism of the experiment, they are indistinguishable. Okay, so a typical example is a coin toss. When you toss a coin, you can see whether it comes out head or tails. But as far as the coin toss itself is concerned, if the coin is well balanced, there's no difference between the two. And in that case, it's very natural to assign the same probability to all these outcomes. So in this case, there are two possible outcomes. And so each of them has probability a half. Right? So that's symmetry. That's very easy to understand. There's a second guiding principle in probability, which is somehow much more subtle. And that's the one I want to spend more time on today. And that's universality. What universality says, it's more of a sort of a general guiding principle of modern theoretical physics, actually. And what it says is that very often if you have a random outcome of some system where you have many microscopic random subsystems that kind of interact with each other in such a way that all of these subsystems, they all do their own thing, they all look more or less similar, they're all somewhat independent, but they interact with each other, and they all combine together to produce some large random outcome, then very often this random outcome, the law of this random outcome doesn't actually depend very much on the details of what these microscopic systems do. And the prime example of this, which many of you would be familiar with, is the central limit theorem. Okay, so the central limit theorem says that whenever you have somehow sums of independent random events, you often have this bell-shaped curve coming up, right? If you look at the probability distribution of the outcome of summing up various random events, you tend to get some bell-shaped curve. And, well, this was actually one of the first people to come up with this bell-shaped curve was actually Demoivre. So I think that's kind of fitting for today. Quite some time ago. And one way you see it, for example, from coin tosses is the following thing. So say I perform 100 coin tosses, and I count how many heads I get. Right? So then most of the time it will be sort of roughly around 50, but occasionally you get 52 or 47 or whatever. And now you perform that experiment 1,000 times. Okay? And you plot a histogram of the values that you get. So here, what this would mean, so here I ask a computer to perform that experiment, and the red crosses are sort of the outcome. And so what you see here is that maybe out of these 1,000 runs, most often you actually got 49 heads. Then here you got 50 sometimes you got 51, etc. But it's relatively unlikely that you get 60 or 65 also. That basically never happens, right? And now if instead of doing 1,000 runs, you do 10,000 runs, well, these red crosses, they sort of align more and more in a kind of smooth curve. If you do 100,000 runs, you get something like this. So you have this nice smooth curve appearing, and that's this Gaussian distribution, which appears very often in probability theory. And that's somehow the most basic example of universality. But what I want to talk about today is, in some sense, more analogs of this that don't just describe one random value, but a whole somehow random field, or random process, or if you want, like a random picture. And the first example of this is actually the discovery of what's called now Brownian motion. And so Brownian motion was something that was observed by Brown. So he was a British botanist back in the early 19th century. And so what he was doing is that he looked at pollen under a microscope. And what he observed is that if you look at the motion of pollen under a microscope, even if the pollen is suspended in water, and what you see is that it kind of performs some little kind of erratic motion under the microscope. And that's the case even if the water is completely at rest, you left it overnight, you made sure that there's nothing, there's no vibration, no nothing, and it still performs this jiggery motion. So what he thought in the beginning is that maybe these little grains were actually alive, that they were actually little animals. But then he figured out that that wasn't the case. And the explanation that then was sort of gradually accepted was that matter is made of atoms and molecules. In particular, water is made up of water molecules, and that wasn't clear at the time. And if you want, the temperature of the water is really something like the average speed of these molecules. So these molecules, they really run around, sort of they bounce around a bit like billiard balls. So they bounce into each other. And the only reason why when water is at rest, you have the impression that nothing moves is just because on average it doesn't move. But actually, if you were able to see the individual molecules, they would run around at very high speed like billiard balls bouncing off each other. It's just the average velocity that's kind of zero. And so when you take one of these grains of pollen in the water, well, it keeps on having these molecules bouncing off it. And so every time a molecule bounces off it, it gets a little kick. So it moves in one direction. But this kick is, of course, tiny because just one single molecule doesn't have much of an impact. But there are many, 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 many molecules, right? And so altogether, the cumulative effect of all of these water molecules bouncing on that grain of pollen is sufficiently strong to actually make it move. But then it moves in a random way. There's no reason why it would move more in this direction than in that direction, because everything is somewhat symmetric, right? And so it performs this random motion that goes, simultaneously in all directions in some sense, and that's the motion that Brown was observing. And then later, in the early 20th century, Einstein and Smoluchowski, they simultaneously, more or less simultaneously, in 05, 06, came up with a more quantitative description, which in particular predicted how far the grain of pollen would travel on average in a given instant of a given interval of time. And so this was a quantitative prediction that they came up with based on, again, the assumption that matter is made up of molecules, which even at the time was, it was relatively well accepted, but there hadn't been a conclusive experiment to actually prove that matter is really made of molecules, because you couldn't just look, because they're too small. And so these experiments, well, a few years later, Perrin, a French scientist, he actually did the experiment. So it was there's a very nice memoir. You find it online. It's been scanned and it's open access now, so you can just download it online. It's a very nice memoir in which he explains how he does the experiment. It's not that easy, because you have to be very consistent, because by how much these particles travel depends on their diameter. And so you have to figure out a way of producing consistently lots of very small particles that all have exactly the same size. And with early 20th century kind of technology. So, well, he managed to do that, and the prediction really fitted. And so that was the first conclusive, if you want, proof that matter is really made of atoms and molecules, and Perrin got the Nobel Prize for that in the 20s then. Now, mathematically, so I just wanted to mention, so this is another French guy who's involved in this story, which is that, in some sense, the same mathematical object, which is this Brownian motion, also arose completely independently in the works of Bachelier. And so Bachelier, he was a French mathematician who was interested in, well, what now you would call mathematical finance. But that was around the same time, so it was in the early 1900s. And so what he did was he was interested in the fluctuation of prices on the stock market. And so he wanted to come up with some kind of theory that explains the fluctuation of prices on the stock market. And he came up with a story which is pretty much the same as the story I just told you about the little molecules of water bouncing off the grain of pollen, which is that he was saying, well, what influences a stock price? Well, it's offer and demand. So, there are thousands and thousands of people who trade that stock. Every time somebody sells the stock, well, the demand goes slightly down, but because there's a little bit more stock available, and therefore the price will go down a little bit. Whereas every time somebody buys some stock, well, there's more demand, and so the price will go up a little bit. Right? And so the people buying and selling stock are a little bit like the molecules of water bouncing off the grain of pollen, and where the stock price itself is a little bit like the grain of pollen being influenced by these random events. Right? And so he came up with a mathematical description of that, which was mathematically essentially identical to the one that Einstein gave in his work 5 years later. And so in both cases, the mathematical description that they came up with is they showed that this random evolution is related to the heat equation. So that's the mathematical equation that describes how heat propagates in a medium. And how is it related to that? Well, imagine your grain of pollen, right? So you have you look at your grain of pollen under the microscope, so you see it somewhere, say here at a given instant of time. And so now you close your eyes, the grain of pollen sort of moves around, and you try to predict where you're going to see it when you open your eyes next, right? So now, of course, you can't predict the exact location. The only thing you can predict is the probability of seeing it in a given location, right? So the only thing you can possibly predict is some kind of distribution of probability of seeing that grain of pollen at a given location. And so one way of describing, and of course, the larger the time you're closing your eyes, the more sort of spread out that probability will be, right? If you open your eyes sort of almost immediately after closing them, well, your best guess would be that it hasn't moved very far. Okay, so then the probability of seeing it in a given location would look very peaked, like this. Whereas if you close your eyes for a long time, well, then anything goes. I mean, it will have spread out very far, and so the probability of seeing it in a given location will be much, much more spread out. And so you have an equation that describes how this probability spreads out. It turns out that it spreads out in exactly the same way as heat spreads out in a solid, in the sense that if you take a cold solid and then you heat it up at a given point, and then you ask yourself how that heat sort of spreads in the solid, it's exactly the same equation that describes that than the one that describes how these probabilities spread out. And so this was actually discovered by Bachelier in his PhD thesis in, I don't know, 1900 or 1901 or something like that. And he's kind of it's an interesting story because, in some sense, he actually founded mathematical finance, but he was, maybe half a century too early or something like this. I mean, so people weren't really interested in what he was talking about. And, well, he got a position at the Sorbonne after he defended his PhD, or a few years later. But then that was actually when World War I broke out. So then he had to go to the army. So he lost his position. And when he came back, the position was, I don't know what happened, but somehow he didn't get the position back. And for a very long time, he actually didn't really have a proper job. And eventually he got a job, I don't remember where, Besançon or something, by the time he was in his 50s or something like this. But then, other people kind of got the Nobel Prize in economics for work which essentially is that work. Anyway, so now, so we have this erratic motion which describes, on the one hand, stock prices on the stock market. On the other hand, it describes sort of the evolution of that grain of pollen in water. It's now, you want to have some kind of a proper mathematical object that describes this. So we've seen it's related somehow to this heat equation, but this heat equation only describes these probabilities of close your eyes, open your eyes an instant later, and then where has that particle gone. What you would want instead is to describe really the probabilities of seeing a whole trajectory of these particles. So what do the trajectories of the particles actually look like? And this was first done by Wiener in the late 20s. So he was a professor at MIT. So he gave, in the 20s, a full mathematical description of Brownian motion, really as a probability on trajectories, which is then mathematically a much more subtle kind of object. He was also an interesting guy, by the way, because he's very well known in probability theory because of this construction of what's called now the Wiener measure. But he's actually also very well known in robotics and cybernetics. Actually, he came up with the word cybernetics. And he's also quite well known in digital signal processing, because he came up with one of the first noise filtering algorithms. And as a matter of fact, one of his PhD students was Bose, who is the Bose of the noise-canceling headphones. And then, so later in the 50s, so here is what these trajectories kind of look like. Okay, so that's a typical trajectory. And you see when you look at stock market prices, well, locally they kind of tend to look like this, right? So let me, just show you. So here, so this is one of these trajectories of a Brownian motion, right? So if you take one of these Brownian motions, so that's one single trajectory of position as a function of time. And what I'm doing here is I take this single trajectory and I'm zooming out at larger and larger scales. And what you see is that it always kind of looks the same. Right? So I can zoom out as much as I want. It always sort of looks the same, but it always looks interesting somehow, right? I mean, in the sense that a straight line also always looks the same when you zoom out, but it's not quite as interesting. Or a parabola, like this parabola here, if you zoom out in the correct way, it also always looks the same. Okay? It's also not quite as interesting. Here, the reason why I drew that parabola is because the way of zooming out for which this Brownian motion always looks the same is the same as the way of zooming out for which that parabola always looks the same, in the sense that if you zoom out by a factor 4 horizontally, you have to actually zoom out by a factor 2 vertically and not 4. Right? So the horizontal zooming is a bit different from the vertical zooming. So it's the thing that keeps that parabola fixed. Okay. So then the fifth is Sodomska. So he was one of the first people to sort of provide mathematical statements that show that these random trajectories, so this Brownian motion, has a kind of universal character in the sense that we've already seen it in the sense that it shows up in the description of pollen suspended in water, and it also shows up in the description of stock prices. Right? So these are two a priori completely unrelated topics. It shows up in both. And the reason is that whenever you have some random trajectory which evolves by performing a motion which in a way just is locally somehow random, but it doesn't really care about where you are, what your position is at a given instant of time to decide how you're going to move next. Under very weak conditions, when you look at this at large scales, it's going to look like this Brownian motion. Now, so I think, is this Brownian motion the only universal object like this? Well, obviously not. So there are other universal objects showing up in probability theory. And so, for example, you can ask yourself, what about 2-dimension? In the sense that, so Brownian motion was a random function of time, just, okay? And time is 1-dimensional. And so now what if you replace time by space? Okay? Say a 2-dimensional space. So what about the random function? What is a natural random function on the plane? So for example, one thing you can do, you see one way you can obtain Brownian motion is in the following, is by performing what's called a random walk. And that's just a random function from the integers to the integers, which has the property that the next value is always either the previous value plus 1 or the previous value minus 1, and these just arise with equal probability. So you just do coin tosses, and if you come up head, you make one step to the left. If you come up tail, you make one step to the right, and then you look at this at large scales, and then you get Brownian motion. So a 2-dimensional analog of this could be the following. So take a nice 2-dimensional graph like this. So for example, this honeycomb graph, or you could just take the square lattice. And so it's a graph which has this property that it's bipartite, so you can color it in 2 colors in such a way that every edge always connects one color to the other color. Okay, so that's what you see here. So blue is always connected to red and vice versa. And now you can look at a random function which has the property that the value at a point is always 1 off from the value of any of the neighbors. Okay, in the sense that if you take any of these edges and you compare the value on one side of the edge, the blue side, to the value on the red side, the difference is always either plus 1 or minus 1. Okay? And so you just look at all possible functions like this, and you pick out one at random. Okay? Same probability, all of them. And then you ask yourself, if I do this, and I make this grid very, very large, right? If I just have a finite chunk of grid, there are basically just finitely many functions like this. If I say I set it to be 0 here or something like that, and there's only finitely many of them, you just pick one at random. you make that grid really, really large, and then you can ask yourself, does that converge to something? Will you see some sort of universal object as you make this very large? And, well, here it already becomes much trickier. So the answer is yes, but we don't even have a proof of it. So you can do simulation. So the picture doesn't look that great here, but anyway, so this here is an actual simulation of what I just described here, whereas this here is a simulation of what is naturally conjectured to be the limit that you should see if you make that grid kind of infinitely large, which is an object called the free field. So here you see, so this is essentially a random kind of function on the plane now, except that things are already a bit more subtle in the sense that it's actually not a random function, but it's what's called a random distribution. And what this means is that actually evaluating at points doesn't really make sense. And the way you see this here is you see that, if you look at this picture from sort of very close up, you see that even in the kind of light regions, there are lots of little dark points, and even in the dark regions, there are lots of light points. So which shows that, so here the color is, of course, just the value of the function, right? And so what this shows you is that the function kind of oscillates like crazy. And so if you were to increase the resolution of this picture, well, you would have more and more sort of, dark points in light regions and vice versa. So in some sense, the values would actually just fluctuate more and more at any given point. And so if you just try to actually evaluate the value at a fixed point, it would never converge to anything. So if you keep on increasing the resolution, and at any fixed point that you look at, the values would just take larger and larger values, both positive and negative. However, the thing that actually does converge to something is little averages. So if instead of looking at trying to get the value at a point, you say, well, I look at the average value in a little circle, for example, then that average value, as you increase the resolution, would converge to some nice limit. So that's what's called a random distribution rather than a random function. So it's already a kind of more sophisticated type of object because it behaves a bit like a function, but you can't actually evaluate it at points. But it's still an object that has a description similar to the Brownian motion, which is a description completely in terms of this Gaussian distribution, which was that bell curve that we saw at the very beginning on the first slide. Now, in both cases, so both in the case of Brownian motion, in the case of this free field, it's possible to obtain this object. It's some kind of a free object in the sense that what you do is you put up some kind of constraint. So in this case, the constraint was just that the values at neighboring points are the difference between values is equal to plus or minus 1. And then that gives you a whole bunch of possible functions here, and then you just pick up one at random. Okay, and you don't care about which, you don't make one of them more likely than the other one. You just pick them all with equal probability. And so when you do a procedure like this, the tendency is that the kind of limit objects that you obtain in this way, they tend to be described in terms of Gaussian distributions. And so they are what mathematicians call free objects, or free fields. Now, here is an example of a situation where, as you zoom out to larger and larger scales, you again see some kind of universal objects, but that object is not free. And so the example here is the example of interface growth models. So if you take so the kind of situation that you should have in mind is a situation where you have so you're again in 2 dimensions. And now in your plane, you have 2 different regions. And the 2 regions are separated by some interface. Okay, so there's let's say, a plus region and minus region. and there's a one-dimensional interface that separates the plus region from the minus region. And what you're interested in is the fluctuations or the evolution of this interface that separates the two regions. And, well, so the kind of model that you can look at is the following, for example. Okay, so here, right, so that's one example of a model of that type, where here you have one region here, which is filled up with Tetris bricks, and one region up there, which doesn't have any Tetris bricks yet. And you just have Tetris bricks falling from the sky, and so they fill up a larger and larger region. So here you don't really see much. So here you see a little bit better what's going on. Right, so here now you clearly see two regions. Right, so there's one region here which is filled up with Tetris bricks. And there's one region here which is empty. And you have new Tetris bricks falling from the sky, and now they go really, really fast. And we are kind of moving up so that we always somehow see, so that interface appears not to move very much. And now what one is interested in is the description of this kind of random interface between the two, and also about how it actually evolves as a function of time, right? And the claim, let's have something like this. And the claim is, again, that the fact that I took Tetris bricks here is completely irrelevant. Okay, so the claim is that you can, whatever prediction you make for this model here should be true for pretty much every model that describes a situation of that type. Okay? So people did actual experiments with liquid crystals. Okay? So what they did is they took a liquid crystal. It's a little bit like what you have in a mobile phone screen. So you have a two-dimensional, very thin two-dimensional film of liquid crystal. And it's one that comes in two different phases. And the two different phases have different optical properties. So you can actually literally see the difference between the two under a microscope. And one of the two phases is more stable than the other one. And so what they did is they prepare it in the unstable one. Okay? And then they zap a laser beam at this two-dimensional liquid crystal. So you have this two-dimensional film, which, where you see that it's in the unstable phase. Then you zap a laser beam through it horizontally. And so the laser beam gives it enough activation energy to go into the stable phase. So then it changes its optical properties on a thin line where the laser beam hit it. And then the stable phase, being more stable, actually invades the unstable one. So that line then kind of broadens out. And you can just take pictures of that, 10 or 100 times a second or something. And then trace out the boundary between the stable and the unstable region, which you can see on the picture, and look at how that evolves as a function of time. And whatever measurements you perform on that match very well the analogous measurements that you would do on this model with the Tetris bricks, which, of course, looks like it's completely unrelated, because obviously liquid crystals are not made out of Tetris bricks. But the mechanism that makes the interface grow is sufficiently close that this universality kicks in and says, well, the two models, or that model, and if you want the reality of the liquid crystal, they fall into the same universality class, which says that at very large scales, you see the same behavior for the two. Yeah? Oops. Okay, so in this particular case, you can come up with a whole bunch of different little mathematical toy models that are supposed to model the growth or the fluctuation of an interface. And you can compare the outcomes, and you can see that they all have the same features when you look at them at large scales. Now, it turns out that in this case, it's even harder to actually prove anything about that. So in the previous case, in the case of the free field, I told you that for that specific model, I mentioned to you, well, there's no proof that it converges to this free field at large scales. But there are many other models that look somewhat similar for which there is a proof. Here, there is one single model for which there's a proof. So that doesn't really give you much of a universality statement. So there's one single model which happens to have lots of other nice properties that are, in some sense, unrelated to the properties you want to study. So they are all sort of accidental properties, if you want. And it has sufficiently many of these accidental properties that you can compute everything. And so for that specific model, which in this picture is this one, actually, for that specific model, you can compute everything. And so very recently, about a year ago, there was a paper where people managed to give a complete description of the asymptotic behavior of this model when you look at it, if you sort of zoom out infinitely far, if you want to show, to describe, give a complete description of the limit that you see. There are sort of partial statements for a bunch of other models, and they also rely on these kind of accidental additional nice properties. But for most models like these Tetris bricks, or the kind of model that looks like that here, for most of these models, there's no mathematical proof of anything, pretty much. And so you would like to still have some way of mathematically understanding this concept of universality, right? So it seems extremely powerful because it predicts that there are these very large classes of models that all have the same behavior at large scales. And it's really sort of underpins theoretical physics. But mathematically, it's very, very poorly understood. So we understood very well the central limit theorem and variants of the central limit theorem. And that's somehow these free models in some sense. But these interacting models are very, very poorly understood. And there are only very few of them for which one can say anything, right? So one can at least somehow give some kind of statements of like, if there were a limit, what are the properties that you would expect? And then you can go and ask yourself, are there many mathematical objects that actually have all of these properties so that they are realistic candidates for the kind of limits that you could possibly see? And so, so there are a few properties that you can collect like this. So one property is scale invariance, because of course these objects are obtained by zooming out. And so if you get a limit under the operation of zooming out, the limit that you get has to be itself invariant under the operation of zooming out. So that's clear. It's usually because you talk about things that get updated in some kind of local way, you expect to see some kind of Markov property, at least for the mathematicians in the audience who know what this is. And then if you start with something which is of translation invariant, then of course it would stay translation invariant in the limit. If you start with something which is rotation invariant, then of course it would stay rotation invariant in the limit. Now, if you have rotation invariance and scale invariance, then that gives you something called, or at least that suggests that you have something called a conformal invariance. And that's a very much, so in 2 dimensions, that buys you a lot, because there are lots of what's called conformal maps in 2 dimensions. And so that's why in the specific case of 2 dimensions, where you look at models that are rotation invariant, there you can say a lot of things about the kind of limits that you would get. And they're all described by a class of objects that are called conformal field theories. And so there are a whole bunch of probabilistic objects that are related to these conformal field theories and that were investigated in the last sort of 15, 20 years. So maybe some of you have heard about these SLE, for example, which is one particular way of constructing conformal invariant random curves. So in two-dimensional, a lot is known because of that conformal invariance, which buys you a lot of symmetry. If you don't have this rotation, so for example, in the interface growth models that I showed you, that is two-dimensional in the sense that there's a one-dimensional time and a one-dimensional space. Right? So it's two-dimensional. But there's obviously no rotation invariance because time and space, well, they are time and space. So they really don't play the same role at all. So it's not rotation invariant under sort of rotating in space-time. So there, for example, that doesn't fall in this category. Or, our world is three-dimensional. And so in 3 dimensions, well, you expect also to have this conformal invariance, but that buys you much, much, much less because there are much less conformal maps in 3 dimensions. So one thing you can do is you can say, well, there's a class of these objects which we understand fairly well, which are the free ones or the Gaussian ones, somehow the ones that are described by bell curves. And then we don't understand so well the other ones. So maybe we could try to understand at least, something that somehow connects them. And so that's what we call crossover regimes. So the idea here is you take a model which falls into one of these Gaussian universality classes or one of these free models, and then you perturb it a bit. Okay, so you look at a model which is almost the same, but it's a little bit different. So you have a small parameter that allows you to tweak the model. Then if you take that slightly perturbed model, well, maybe you can choose the parameter in such a, you can choose the perturbed model in such a way that it immediately kicks you into a different universality class. Well, of course, if the perturbation is very small, then as you zoom out, well, at least on pretty large scales, you're not going to see much of a difference between that model and the one you started from, the unperturbed one. And that one, it was the one that was supposed to look like something Gaussian, which you understand very well. And it's only if you zoom out somehow much, much further that then suddenly you start to see a difference between the two. And so the idea is that then maybe what you can actually describe or understand mathematically is the transition at which point you start to cross over from one universality class into the other one. Maybe this transition is somehow easier to understand mathematically. So let me show you again on a movie what I sort of mean here. That's a different one, right? So here this is one. Okay, it's one particular model, which is it's quite different. So here it somehow looks a little bit like this Tetris of model type thing, but actually it behaves quite differently. So let me show how this one behaves at large scale. So this is in a different universality class. Because here, if I look at the large scale behavior, it looks like this. And you see, it behaves very differently. Right? So in particular, before in the Tetris model, when you looked at large scales, it still looked like more or less like a continuous curve. Here it doesn't. Right? So you have these kind of discontinuities forming. So it behaves very differently. Now what I can do is there's a small parameter here. So I take a very small value of the parameter. So this was value 0 of the parameter, if you want. So now I take value 0.01, because you haven't seen any difference. Right? So 0 is this, 0.01 is this. You don't see any difference at all, obviously. Right? So if I take this value 0.01 and I zoom out, so again, here it still looks the same as 0. Right? So here I go to 0, 0.01. I don't see any difference. Right? But if I zoom out really far, I see that it actually behaves quite differently to to what I had before. Right? So now, at this scale, I see that it actually behaves much more like the Tetris model. Right? You don't see these big discontinuities anymore. And it kind of looks like this kind of continuum curve. And the conjecture is that, at very large scales, this actually behaves like the Tetris model. So, right, so that's the sort of thing that I'm talking about when I talk about this crossover regime. Right? So you take a model which is in one universality class, you have a parameter, you tweak it a tiny bit. In the beginning, you have the impression that you haven't changed anything, but if you zoom out sufficiently far, at some point, you see that you actually have changed it quite substantially, that it's really in a different universality class. And then you can ask yourself, if you zoom out, there's a transition somewhere, right? So up to a certain scale, it looks like it were in one universality class, and then starting from a certain scale, at some point it starts to look like it's in a different one. And then you can ask yourself, if you go at just the right scale where it switches from one behavior to the other behavior, is what you see at that scale, is that itself universal? Right? So do you always see the same thing there? Right? So given these two universality classes on each end, is the thing that switches between one and the other one, do you always see the same, or are there many, many different ways of switching from one to the other one? It turns out that this is itself kind of universal. Okay, so this switching is described by a bunch of what are called stochastic partial differential equations. So they are partial differential equations like this, but with some random terms. So here this psi is something called white noise, which you can kind of think of it as something random where you have independent random variables at every point in space-time. And then you can ask yourself, can I prove that sort of statement mathematically? Right? So can I prove that, take one of these models that belongs to this Gaussian universality class, of which I kind of understand the large-scale behavior, tweak it a little bit. Can I actually prove mathematically that the tweaked model, if I look at it at the right kind of scale, looks the same as the solution to one of these stochastic partial differential equations? And this, it turns out, is much more amenable to mathematical proofs and to some kind of quite general sort of theory. But it's still tricky, and the reason why it's tricky is because, so let me show you a movie again. So here, that's the solution to one of these. So that looks a little bit similar to this free field I showed you earlier, right? And so this is actually one of these stochastic PDEs, which describes the transition between the free field and another universality class, right? The Ising universality class. And so what this means is that the solutions to this equation, locally, they're going to look like this free field, but globally, they're going to look different. Here, you actually see that in the sense that these dark and light structures have somehow much more interesting shapes than in the case of the free field. And so here, the equation that described this is this equation here. But you see the problem with this equation is that on the right-hand side, you have the cube of the solution appearing. And remember what I told you about the free field, which was that it looks like a random function, but it actually isn't. You're not really allowed to evaluate at points. Okay? And so then what does it mean to take the cube of it if you're not allowed to actually look at the values? Right? You can only take the cube of something which has values. Right? You can only take the cubes of actual real numbers. Right? And so then it's just not clear at all what this equation even means, because there's a cube of the solution on the right-hand side, but the solution can't actually be evaluated at points. So it's not clear what it means to take the cube of the solution. And so here in this case, one consequence is that actually this constant here that appears in the equation has to be kind of infinite. And this is really some sort of infinity that's there to cancel out another infinity that comes from trying to take this cube of something that takes infinitely large values. Okay, and so even figuring out what these equations mean is it's kind of a subtle business. Okay? And then, of course, you want to show that, actual kind of little microscopic toy models that you play with really converge to the solutions of these equations. I mean, in order to be able to prove that, well, you first have to at least say what does it mean to be a solution to this equation, because otherwise your statement doesn't make any sense. Okay? And so let me just, to finish, I can show you okay, so that's just the last slide. I can just show you some kind of general statement that we've built over the last 4 or 5 years. So now there's kind of a collection of results, and it's sort of been various joint works with various people, some of them in the audience. And so we have now a relatively general theory that allows you to prove statements of that type. So at least there's a very general theory that allows to build these objects. Okay, so let's say, what does it actually mean to be a solution to this equation, which doesn't appear to make any sense a priori. So this, we have a quite general theory now. We don't yet have a good general theory that really allows to prove the kind of statements that we're really after, which is have a quite general statement of the type that I was trying to explain. So take a general model, which is in this Gaussian universality class, perturb it in a more or less arbitrary way, zoom out to the right scale, and then prove that it's given by one of these stochastic PDEs. We don't have it's not clear how you would even formulate a statement like that mathematically. But people start to have various statements that go somehow in this direction. I think it's kind of an interesting thing to look at. And I think I should stop here. Thank you very much.
Thank you for the wonderful lecture. Are there any questions?
Yes, I have one. So this concept of university class, does it have a rigorous mathematical definition? Because I have seen a lot of physics papers speaking of university class, but I have the feeling there was no proper mathematical definition.
No. No, I mean, it's one of these things that, you know what it is when you see it, right?
Any other questions?
Yeah.
So in the videos you showed, there's these kind of streaks going like down like that. Can you explain what that is?
Yeah, so, okay, actually these streaks, so you see them also in this model. So, okay, so let me, oh no, it's not here anymore. Right. Right, so here you see these you have these sort of streaks here. So here the model here is something called ballistic deposition. So the way it works is you have just little bricks falling from the sky, a little bit like in the Tetris thing, but now the bricks are just single bricks, okay? And the rules, the way they pile up, it's a little bit different from Tetris in the sense that they don't just pile up on top of each other, but they also stick to neighbors. Okay, so if you already have a brick here, a new brick falls down, and then here it would just stick to its neighbor. And that's the mechanism that kind of creates these streaks, because once you have an overhang somehow, right, then new bricks kind of falling down, they would increase the size of the overhang because of that sticking mechanism. And that's what creates these these streaks like that.
Any more questions?
Out of interest, what was the parameter that you perturbed to change the universality class in one of the models?
So in that, yeah, I can show you afterward. I mean, I can write down what the model is. So it's relatively easy to, but you need a piece of paper. Yeah.
Just to follow up on the previous question about universality, isn't there even a possibility to be linked to the universality concept in category theory? Like some limiting behavior between similar structures, and at the end, you end up with.
Yes, no, sure. I mean, in the sense that, right, I mean, it's somehow this general idea that as you somehow take limits, so in some sense there are not as many possible limits that you can get as you have models to play with at the beginning somehow, and so therefore every possible limit has to have lots of models that have the same limit. Sure, in that very, very general sense, maybe. Yeah.
Are there some domains of application of these models, like what we think both in physics or biology?
Yeah, so I already mentioned the actual experiment, right? I mean, I lost my pointer. Oh, here's the point. Right, so this here is actual experimental data from that experiment with the liquid crystal, right? And this here is actual experimental data from a similar experiment, but where people, instead of taking liquid crystal, they took a sheet of paper, and then instead of zapping it with a laser, they had a little electric wire at the bottom of the sheet of paper. They zap a current through the wire, and that ignites the paper. And then the paper is sort of like cigarette-type paper, that sort of paper, so it doesn't really burn with flames, but it just sort of consumes itself, a bit like cigarette paper, right? And so you ignite it at the bottom with that electric wire, and then it kind of burns upwards. And then that's the position of the, of the front at different successive times. And again, there are certain, because here the data is all very coarse, so, but there are things you can extract out of that data that kind of match the same kind of models, right? So in that sense, I mean, so since they're quite, well, since the whole point is that these are kind of quite universal objects, so they show up in various contexts. Right? So if there are various contexts that behave in somewhat the same way, you would have the same model applying.
If you go back to your streak, the previous slide you showed with the streaks, if you regard those as voids, then you could characterize the size of the void, and then you've got clearly a few big ones and many, many, many small ones. Is there any relevance to the distribution of the size of a void? Is there some kind of central limit theorem operating which gives you the distribution of void size?
I think you can get, so I've never actually done the exercise, but I think from the, so there are various exponents about, for example, like after a certain amount of time, how big are these valleys and mountains? So this you kind of know, and you know how wide they are. And from this, so you kind of, that since the total number of bricks that fall down at a given point is always more or less the same everywhere. And so if you have a big mountain here, it means that you have to have you have to have more voids underneath the mountain than underneath the valley somehow, right? Because the number of bricks that fell down is about the same. And so from these sort of considerations, you could probably more or less, you might be able to extract some exponent about the size of these voids. I mean, they probably do get larger and larger as you wait for larger times, and I suspect you would be able to extract some scaling exponent out of it.
How do you come up with these exponent 3 or 4 equations? What's the interpretation?
So there are, right, so you mean these scaling exponents, so they somehow tell you, right, so they tell you here the sort of various sizes of these features. Right? So for example, in this KPZ universality class, you have exponents 1/3 and 2/3 showing up. And what they tell you here is that if you look after time t, so once the height of the pile of bricks here is about t, the height of these little mountains is about t to the 1/3, and the width of the mountains here is about t to the 2/3. So these kind of scaling exponents, they relate to kind of sizes of features. Yeah.
If there are no more questions, let's thank Professor Heirer again for his lecture.